Hello everybody, and welcome to our video on the integral and comparison tests. Okay, so we're going to dive right into the integral test here, and the statement for the integral test is: suppose that f is a continuous positive decreasing function on an interval from a to infinity, and let a sub n be equal to f at those integer values of n. Then the series from n equals k to infinity of a sub n is convergent if and only if the improper integral from a to infinity of f of x dx is convergent. In other words, if the integral from a to infinity of f of x dx is convergent, then the series of a sub n terms converges as well. And if that integral is divergent, then the series of a sub n terms is divergent. So we can basically sum this up in the picture below. So here we've got this function f, and each of these rectangles we've drawn has a width of 1 and a height of f of 1. So this height is f of 2, so forth and so on, which means the area of each of these rectangles is equal to the value of the function at that point, or in other words, a1, and a2, and a3, and a4, and so forth and so on. So the sum of all of these terms for our series is bounded by the area under the curve. That's what this says. The sum of all of the terms, if I add up all of these areas for these rectangles, that's bounded above by the area of the integral. So if that integral is convergent, then that sum must also be convergent. It must also be a finite number. Now, the second expression, we need a slightly different picture for. So here, we start with the assumption that that function is divergent. And in that case, again, remember, we're starting with the assumption that the integral is convergent or divergent, and then we're placing our rectangles for our series based on that. So if I know that the area under this green curve is infinite, that it grows unbounded, then I can change the placement so that I move all of my rectangles representing my series to the right, and see that since the area under green, the green expression, or the green function, is infinite, the area formed from these rectangles, which is the same as the sum of the infinite series, will be infinite as well. All right, so that's all the integral test says, but there is these conditions I do want to emphasize are very important. F has to be continuous, positive, and decreasing for this to make sense. If your integral for f was ever increasing on your interval, that would be a problem, or at least if it was increasing repeatedly. Notice that the way we've written this is that as long as it's increasing, continuous, positive, and decreasing, on some interval from a to infinity, it's totally fine. So in other words, if my function looks something more like this, this would be totally fine. I would just have to pick this point A to start my integral test and see that that's finite or infinite. And the reason that that's totally fine is because when I look at a series of terms, when I add these rectangular areas together, I'm guaranteed that this area up before A is finite. There's no way for that not to be finite. It's a finite number of rectangular blocks. What I'm concerned with is what happens in the long run. So as long as we can find some point where the integral or the function is continuous, positive, and decreasing past that point, then I'm totally fine to just take that integral, that improper integral from that point onward, and use that to check the convergence or divergence of the series. Okay, so let's go ahead and dive into an example. Determine if the sum of the series below is convergent or divergent. All right. Well, we've got n equals 1 to infinity of 1 over n squared. And so we're going to let f of x here be 1 over x squared. This is the same thing as x to the negative second. So if I take f prime of x, I get negative 2x to the negative third, which is negative 2 over x cubed. And what we see is that f is continuous for any x greater than 0, and it's also has a negative derivative for any x greater than 0. Now what I need is some integer, or typically what we will use is some integer point, and we need a closed interval. So this is stronger than what I'm about to write. I can say definitely f is continuous and decreasing. F is continuous and positive and decreasing. Let's try that one more time. Continuous, positive, and decreasing. On the interval from 1 to infinity, including 1. So I didn't say 0 to infinity because I can't include 0 in that statement. So I just started at 1. And so now we can check this with the integral test. So I take the integral from 1 to infinity of 1 over x squared dx. I do need to rewrite that as the limit as t goes to infinity of the integral from 1 to t of x to the negative second dx. And this becomes the limit as t goes to infinity of x to the negative first divided by negative 1 evaluated from 1 to t. That's the limit as t goes to infinity of, okay, so this is negative 1 over x, plug in t, negative 1 over t, minus negative 1 over 1, which becomes positive 1. And this negative 1 over t, when t goes to infinity, approaches 0. So altogether, this limit is 1. That implies that the series from n equals 1 to infinity of 1 over n squared is convergent by the integral test, right? We got that this integral was convergent, and therefore the series is convergent by the integral test. Okay, let's go ahead and move on to our next example. Determine if the sum of the series below is convergent or divergent. So we're going to again consider the function f of x equal to, in this case, 1 over the square root of x. And I can rewrite that as x to the negative 1/2 power. Now, this function is positive for positive values of x. It's also continuous for x greater than 0. And when I take the derivative, we get negative 1/2 x to the negative 3/2, which is negative 1 over 2 times the square root of x cubed. And that's negative for x greater than 0. And of course, again, what are we checking? We're checking that it's decreasing by checking that the derivative is negative. So f is continuous, positive, and decreasing on, now again, these statements are all true for any x bigger than 1, but I'm just going to start with the closed interval from 1 to infinity. And so now we'll take our integral 1 to infinity of 1 over the square root of x dx. And as always, I need to convert this to a limit. The limit is t goes to infinity of the integral from 1 to t of x to the negative 1/2 power dx. Now here I'm taking the antiderivative, so I add 1. I get x to the 1/2 power divided by 1/2, evaluated from 1 to t. And that's the limit as t goes to infinity of 2 times the square root of t minus the square root of 1. And in this case, what do we see? We see that when t goes to infinity, the square root of t goes to infinity. I'm multiplying by a positive number here. So altogether, this limit is infinite. So we say that the integral diverges. And if the integral diverges, that implies that this series from n equals 1 to infinity of 1 over the square root of n diverges by the integral test. Of course, I always want my students to cite any named theorems when they use them. Okay. Well, that's it for example 2. Let's move on to another one. Determine whether the series below converges or diverges. Okay, so what do we got here? ln of n over n. So we're going to let f of x be ln of x over x. And here is where we start to see, okay, well, we're not always going to pick 1 for our interval. Because the natural log of x is positive for x bigger than 1, and not for x bigger than 0. So here, we get that this is positive for x bigger than 1. And what else? Well, we do have continuity for x greater than 0. The natural log is a continuous function for x greater than 0, and so is if we're dividing by x. That doesn't cause us any problems as long as x is larger than 0. And so what do we get for our derivative? All right, we have to apply the quotient rule. So the derivative at the top, that's 1 over x times x minus ln of x times the derivative of x, which is 1 over x squared, I should say. And that's 1 minus ln of x over x squared. So this is positive when, or I should say negative, when the numerator is negative. The denominator is squared, so it's always positive. And if 1 minus ln of x is negative, that implies 1 is less than the natural log of x. So I need to know what x values give us the natural log being larger than 1. And that's e to the first power, right? ln of e, or ln of e to the x is x. And the natural log is an increasing function. So I know once I cross e to the first power, all of my values for the function will be bigger than 1. So that implies that x would have to be bigger than e, which is roughly 2.7-ish. So, in summary, f is continuous, positive, and decreasing for x, I should just say for on the interval for 3 to infinity, right? So I'll just go to the next integer up from e, and then we're good. So now we can apply the integral test. And we look at the integral from 1 to infinity of ln of x over x dx. I said 1 to infinity, even though we just showed that we need to start at 3. Now, it wouldn't have changed anything because integrating from 1 to 3 on this function is going to give you a positive finite result. So it doesn't actually affect the final answer. But in terms of making sure that the theorem is being applied on the appropriate interval, we just want to have good habits. Now, when it can affect the answer is if you applied this test where there was also an asymptote. Like if you changed your bound past 0, you'd be including that asymptote there, and that would really cause problems. Okay, anyways, moving on, we've got the limit as t goes to infinity of the integral from 3 to t of ln of x over x dx. And so I've got to do a u substitution, which I'm going to write up over here. U is going to be ln of x, which makes du 1 over x dx. And so u evaluated at 3 is just ln of 3, and u evaluated at t is ln of t. And so I apply my substitution. Still have the limit as t goes to infinity, but our bounds change from 3 to t to ln of 3 and ln of t. And then I get u du inside the integral. So a nice, easy integral to evaluate. That becomes u squared over 2, evaluated from ln of 3 to ln of t. And that's the limit as t goes to infinity of 1/2 times ln of t squared minus ln of 3 squared. And the natural log, when t goes to infinity, the natural log goes to infinity. And so when I square that, it's also approaching infinity. And so this whole limit is approaching infinity. And that implies that our series for ln of n over n, and I'm trying to remember where we started. That series started at n equals 1. Diverges by the integral test. Okay, that's it for that one. Now we're going to move on to a very important theorem. And this theorem is called the p-series test. So we're going to use this a lot throughout this section and the rest of this chapter of material. So the rest of our discussions on series, this is going to come up constantly. And the theorem's statement is very simple. The series of the form from n equals 1 to infinity of 1 over n to the p is called a p-series and is convergent when p is greater than 1 and divergent when p is less than or equal to 1. Okay, so let's go ahead and prove this. Now, believe it or not, we've actually done the hard part of this proof previously. So for p being greater than 0, we get f of x is 1 over x to the p. Now this is obviously positive when x is positive. And its derivative will be negative p x to the negative p minus 1, which is negative p over x to the p plus 1, which is negative for x greater than 0. And so f is both increasing and continuous, and I should have also said and positive, on the interval from 1 to infinity, and therefore the integral test applies. So we've already shown in our section on improper integrals that the integral from 1 to infinity of 1 over x to the p dx converges for p greater than 1 and diverges for p between 0 and 1, including 1. Now, the reason I didn't say anything about values of p less than 0 is because when p is less than 0, I can't apply the integral test because the derivative won't be strictly negative. So, at least though we've covered all the cases for p greater than 0, now let's look at the other cases. When p is equal to 0, we get that the limit as n goes to infinity of 1 over n to the p is the same thing as the limit as n goes to infinity of 1 over 1. And that's just 1, which isn't 0, and so the series diverges by the test for divergence. When p is negative, we get that this limit as n goes to infinity of 1 over n to the p is infinity, right? So you could think of rewriting this as the limit as n goes to infinity of n to the negative p, where negative p is a positive power. And then it should be clear that that's going to go to positive infinity. And that also tells us that the series diverges by the test for divergence. So this implies that the series is convergent whenever p is greater than 1 and divergent whenever p is less than or equal to 1. So let's go ahead and apply this theorem real quick. So here we've got the series from n equals 1 to infinity of 1 over n to the 5/4. And we could say this converges since it is a p-series with p equal to 5/4, which is greater than 1, by the p-series test. And below here, we would say for part B, this is the series from n equals 1 to infinity of 1 over n to the 0.7 power. And we would say that this diverges since it is a p-series with p equal to 0.7, which is less than or equal to 1. And that's it. So the p-series is very, very powerful, and essentially for a whole class of functions, these are sequences, or terms, maybe I should say. This whole class, it allows us to skip dealing with the integral test. And of course, we still need the integral test for certain cases like this example 3 we did here, but it at least takes care of a very large subsection of series. All right, now let's go ahead and take a look at another very important theorem, the comparison test. So the comparison test states, suppose that the series of a sub n and the series for b sub n are a series with positive terms. What we mean by that is every a sub n and b sub n term are positive. Now this is very, very important because this theorem does not work if any of those terms are negative. You need to know that every single term is positive or you cannot use this test. It breaks completely otherwise. So we need to know that all the terms are positive if we want to be able to use the comparison test. And what's the conclusion here? It says, if the sum of b sub n terms is convergent, and a sub n is less than or equal to b sub n for all n, then the sum of a sub n terms is also convergent. So if we draw a very quick sketch here to represent case I here, what we're saying is a sub n can be represented by the sums of the areas of these rectangles. B sub n could be represented by these bigger sums of rectangles. So what we're saying is, hey, if the sum of these area rectangles here that correspond to b sub n is finite, then the sum of the blue ones is also going to be finite. Now you can see, hopefully from this picture, why the condition that the terms are positive is really important, because if they weren't, I could have blue rectangles that just went, well, that was not what I wanted to happen there. Let's try that again. I could have blue rectangles that just went wild, like all over the place here. Stop drawing arrows. I'm not trying to draw arrows. I don't even have that feature turned in. I don't know why it does this to me sometimes. Let's try to turn it on and back off again. See if we can get this to act properly. Okay, I'm gonna try that one more time. If we allowed any of these terms to be negative, we could have our second sequence could look like huge rectangles like this, and they could have a negative infinite value for the sum. So we need this bounding essentially by the x-axis to ensure that we still get a finite area there. Okay, similarly, if I just reverse this picture around and say, hey, if b sub n are the terms in light blue and that sum is divergent, then the a sub n terms, which are bigger in this case, are going to also have a divergent sum. All right, so that's the logic or the general idea, but let's actually look at the proof here. So in order to prove this, what we're going to do is first look at some partial sums. So we look at the partial sum for a sub I. That's the sum from I equals 1 to n, and we're going to denote that as s sub n. And the partial sum for t sub n is the sum from I equals 1 to n of b sub I. And so t is the infinite sum, the series of b sub n terms. Okay, so what do we see from this? Since a sub n and b sub n are all positive, that implies that the sequences s sub n and t sub n are increasing. What do I mean? I mean that s2 is a1 plus a2, and s3 is a1 plus a2 plus a3. And since all of the terms are positive, s3 has to be bigger than s2. And the same thing is true for these partial sums t sub n. So both of these partial sums are increasing, and since the infinite series for b sub n is convergent, then t sub n is approaching that value for that series t. The partial sums are approaching t. So what does that give us? Each a sub I is less than or equal to b sub I. So that means the partial sums s sub n, the sums of the a terms, will always be less than or equal to the sums of the b terms. And therefore, the partial sums of the a terms are less than or equal to t. So that tells us that the sequence of partial sums here is both increasing, which we already saw, and bounded, and therefore it converges by the monotonic sequence theorem. And if the sequence of partial sums converges, the series converges by definition. Now in the other case, if the sum of b sub n terms was divergent, then the partial sums are approaching infinity because all of the terms are positive. Since the terms are positive, we know the only way it can diverge is for those terms to add up to infinity, so to speak. And so, since all of the a sub I terms are greater than or equal to b sub I, all of the partial sums for s are bigger than the partial sums t. And so if t sub n is going to infinity, so is s sub n. And therefore, the series of a sub n terms diverges by definition. So essentially what this does for us is allows us to take our previous integration or our previous series convergence tests and apply them to other series via a comparison. So series that they don't really work for directly, we can make comparisons to evaluate the convergence of those series. Okay, so let's take a look at that. Example 5. Determine whether the series below is convergent or divergent. So this is a lot like the comparison test for integrals. And just like that, when we try to figure out what series to convergent to compare it to, we don't want to force the comparison. So I'm not trying to guess, hey, what series should I converge this to? What I'm trying to do is find ways to simplify this expression. And here I know if I didn't have this -7 here, n to the 5th over n to the 6th would be much nicer. Much easier to work with based on my previous tests for series. So, well, that's great. How can I compare these two things then, right? So I've removed the -7. Well, a smaller denominator corresponds to a bigger number, so I should have my inequality facing that way. And of course, n to the 5th over n to the 6th simplifies to 1 over n. And we know that 1 over n is positive. Now, mind you, there is a little caveat here, which is that this is true for n equals 2 and above. If n equals 1, this denominator would be negative and that would be a problem, but this series is from n equals 2 and above, so this inequality holds for n greater than or equal to 2. That's totally fine. Okay, so since the series 1 over n is the harmonic series, and we know it diverges, that implies that this series from n equals 2 to infinity of n to the 5th over n to the 6th minus 7 diverges by the comparison test. And that's it. So now all of these results that we found about general types of series, geometric series, p-series, the harmonic series, which is just the p-series when p is equal to 1, all of these different tests that we've figured out up to this point can now be applied to a lot more general series for determining convergence. Okay, so let's take a look at another example here. Little formatting issue. Should be a little extra space there. Okay. Determine whether the series below is convergent or divergent. So we've got the series of sine squared of n over n cubed plus 1 or plus 2. So again, I want to try to figure out how to compare this to something simpler. And the first thing I think is, well, sine squared of n is positive. I do know that this is positive. It's bigger than 0, and the denominator is going to be bigger than 0 for positive n values. But I also know that sine is at most 1, so sine squared is also at most 1. So I can simplify this a bit by comparing it to 1 over n cubed plus 2. And here, I'm adding 2 to the denominator, so if I get rid of that and I just look at 1 over n cubed, bigger denominator is a smaller number. So that means that sine squared of n over n cubed plus 2 is less than 1 over n cubed. And the series from n equals 1 to infinity of 1 over n cubed converges since it is a p-series with p equal to 3. And of course 3 is greater than 1. That implies that the sum from n equals 1 to infinity of sine squared of n over n cubed plus 2 converges by the comparison test. Okay, so now notice that in both of these cases, we were able to come up with some simpler expressions really nicely, and the inequality went the perfect way, right? Here, we had a bigger thing compared to 1 over n, And since the series for 1 over n diverged, this series would be bigger and therefore also diverge. And similarly here, we were able to find an upper bound, and it happened to be that the series that was the upper bound here also was convergent. And so we had a convergent series bigger than another series, so that series would also converge. So how do we deal with cases where we think we're making the right comparison, but the inequality goes the wrong way? And for that, we deal with the limit comparison test. So the limit comparison test says, suppose that the sums of a sub n and the sums of b sub n are a series with positive terms. If the limit as n goes to infinity of the quotient of the general term a sub n divided by b sub n is c, some number that's both finite and positive, then either both series converge or both diverge. So as long as you know what one of them does, you'll know what the other does. So we'll do a look at a quick version of the proof here. This says let m and n be positive numbers such that c is between m and n. Because a sub n over b sub n gets arbitrarily close to c, right? That's what we mean when we take a limit, it gets really close to c. For large values of n, there exists an integer, cap n, such that a sub n over b sub n is between m and m whenever n is big enough. So if I multiply b sub n across, I get that a sub n is between little m times b sub n and big M times b sub n. And so if the sum of b sub n terms converges, then the sum of cap m times b sub n converges, since it's just a constant multiple. And therefore, the series of a sub n terms converges by the comparison theorem. Similarly, if the sum of b sub n diverges, then the sum of the little m times that converges. Again, it's just a constant multiple. And so that implies the sum of a sub n terms diverge by the comparison theorem. So basically, what am I saying here? The limit comparison test is the comparison test, right? This proof shows you that you're just using the comparison theorem, except that it works when the comparison theorem inequalities aren't correct. So we use this when the comparison test inequalities don't work out. At least if you're sure that you're making the right comparison. So of course, let's illustrate that with an example. Test the series from n equals 1 to infinity of 1 over 3 to the n minus 2 for convergence or divergence. So let's try to set up our comparison as usual, 1 over 3 to the n minus 2. This is clearly positive when n is bigger than 1. And I'm subtracting 2 from the denominator though, so if I try to make a comparison with what I think is the more obviously simple expression, 1 over 3 to the n, a smaller denominator is a bigger number. And so here's the problem. I know that the series 1 over 3 to the n, which I can write as the sum, so from n equals 1 to infinity, of 1/3 times 1/3 to the n minus 1 power, converges by the geometric series test, since the absolute value of r is 1/3, which is less than 1. So what's the problem here? The problem is that this term, 1 over 3 to the n power minus 2, is bigger than 1 over 3 to the n. So knowing that the sum for 1 over 3 to the n is finite doesn't tell me anything about a larger series. So I can't make any conclusion for using the comparison test here. So how can I make a conclusion? Well, I can go, well, I'm pretty confident that I'm comparing to the right series, the correct series, because these are just so obviously related to one another. So then how do I actually check that my conclusion is correct? Well, we'll call a sub n the 1 over 3 to the n minus 2, and b sub n the 1 over 3 to the n. And so then we'll apply the comparison test, which says, or the limit comparison test, which says, take the limit of the quotient, a sub n over b sub n, and see if you get a positive finite number. So the limit as n goes to infinity of a sub n over b sub n is the limit as n goes to infinity, 1 over 3 to the n minus 2 over 1 over 3 to the n. And dividing by a fraction is just multiplication by the reciprocal. So this gives me 3 to the n over 3 to the n minus 2. And it's not really clear how to evaluate this limit, but I can take the same approach I do for polynomial expressions, and I'll multiply by 1 over the highest power of 3 to the denominator in this case, which is really 3 to the n. So that gives me the limit as n goes to infinity of 1 over 1 minus 2 over 3 to the n. This term here, 2 over 3 to the n, is going to approach 0 as 3 to the n gets bigger. And I get left with 1 over 1, which is 1. And this is positive and finite. And that implies that both series converge by the limit comparison test. Again, the limit comparison test says either both series converge or both diverge, and I already know that this series converges by the geometric series theorem, so that my second series has to do the same thing. It has to also converge. Okay. Well, that's it for this video. Thank you for watching.